Hi everyone and welcome back to PrepFusion. I am Anish and today we will be starting with lecture 63 of electrical machine subjects. So today we will start with the new chapter, that is single phase motors. So this was left out. This is a miscellaneous concept. So this is inside the miscellaneous concept chapter. So today we will be discussing about the working principle of single phase motors. Also we will understand the equivalent circuit. Also we will solve few I will give you few questions as homeworks. Okay, like few questions I will do, and in the next lecture few more questions and more about types of single phase motor we will learn in the next lecture. So first of all, what is a single phase motor? So single phase motor is nothing but a three, it is similar, the construction is similar is similar similar to uh, induction motor. Induction motor. Okay. So construction wise it is same, but here instead of three phase supply we will give single phase supply. So here, right, the magnetic field, if I would have given a three phase supply, what kind of magnetic field was developed? If I would have given a three phase supply, the magnetic field that was developed was rotating magnetic magnetic field. Okay, if I would have given a single phase supply, then what kind of magnetic field will you develop, that we will see. Okay, three phase I know we will get a rotating magnetic field. So rotating magnetic field means north south poles will rotate with speed ns. But here what will happen? Here let's assume that at an instant, like this is the one end of the winding and this is the other end of the winding, it's a single phase supply, there is no abc. Okay, just there will be one plus minus. So for a certain instant it's a sinusoidal current, right? I'm providing a sinusoidal voltage which will which will induce a sinusoidal current. So I of t is sinusoidal. So at a particular instant, let's say at t equals to t naught, at this instant here current is incoming and here current is outgoing. It is just two ends of the winding, right? So one end of the winding is here incoming, other end of the winding is here outgoing. Okay, so where will the poles be located? So if I am observing, the poles are like this. So this will be my north pole, this will be my south pole, this is my axis of the magnetic field, right? So what is happening? It is sinusoidal. Let's say current is increasing here. So this is my I of t. This is my I of t. So here what is happening? If current is increasing, then the magnetic field that is going from the north to south pole will increase. So this will also increase, right? Again, current here it will be peak. It will be the maximum here. Then again it is reducing. So slightly the magnetic field will reduce. It will reduce. It will reduce. Then again what will happen? Then again I see current direction is reversing. So if this was incoming and this was outgoing, now it will reverse. So this will be now incoming and this will be outgoing, right? It will just reverse. So what will happen? This will be here. This will be here. This will be here. It is outgoing. Okay. So what is happening? What do you observing with respect to this point? If I see with respect to this point, here the magnetic north and south pole actually are not rotating, right? What is happening? The magnitude of the north pole is reducing the magnetic field. Then again it is going in the opposite direction. So north, what is happening? The poles are interchanging basically. The poles are interchanging. So the field strength will be pulsating in nature. Okay. So what is happening? Like if you see here the north pole, what is happening? The magnetic field strength, magnetic field strength is pulsating in nature. So the magnetic field strength is pulsating in nature. Pulsating meaning for a certain second it is north pole is here, magnetic field is going from here to here, from right to left, then again it is going from left to right at this particular point, right? So it is pulsating, it is not purely, sorry, it is not a rotating magnetic field, so it is a kind of a standing magnetic field. Standing magnetic field. Why standing magnetic field? Because if I plot the phi of t, right, with respect to alpha, what will I get? So here, right, the magnetic field, if I am at this axis, the magnetic field is maximum. Slightly if I move here, here the magnetic field will be slightly lesser than this point, right? Again if I move here, it will be 0 because it is quadrature to the main axis. Again if I move here, slightly magnetic field will be there, but this time the direction is from right to left. Previously if I was at this point, the direction was from left to right, sorry, from right to left. Here the direction is incoming. So what am I telling you? If let's say I'm at this point, if I'm at this point, the magnetic field is going from like outward from this conductor, right? If let's say that the rotor is at this point, the magnetic field is incoming to the conductor, so it is just opposite sign. So with respect to alpha, if I observe, if I'm here, right, when alpha is 90, let's say this is the alpha equal to 0 point. If alpha is 90, then magnetic field will be 0 because it is directly quadrature to the main direct axis. So when alpha is equals to 90, when alpha is equals to 90 degree, basically the flux is 0. Again when alpha goes beyond 90, the flux basically is negative, opposite sign. So what kind of cosine or sinusoidal gives me this kind of characteristics? I know cos, right? In case of cos starts with maximum value at alpha equal to 0, which is maximum going outwards. Then again it reduces, and at 90 it becomes 0, which is exactly correct. At 90 it should be 0. Then again it reduces, goes to negative value like this, right? It keeps on going like this, right? So this is my cos basically. Alpha. With respect to alpha, this is my cos. Okay. So this is my cos alpha basically with respect to alpha. I have got this thing. So how will I plot it? Now remember, your magnitude of the flux also is varying with respect to current, because I know flux phi is proportional to current because it is proportional to mmf. So what is the I? I is function of time. So if I just at this point like this, whatever magnetic field I was noticing when I was stationary at this point, so at t equal to 0 it was maximum, sorry it was 0, then at t equals to pi by 2 it was maximum, t equals to slightly more than pi by 2 it is reducing, so it is reducing and then going in the opposite direction. So reducing then going in the opposite direction. So that is what is happening at this point, right, at this point. So if I am stationary, then the flux is simply a sinusoidal at this point alpha equal to 0, but as I move my alpha, the flux magnitude also will reduce. So basically your phi will be a function of both t and alpha. Your phi will be a function of both t and alpha. So this will be equals to this will be so it will be proportional to phi m of sine omega t into cos of alpha. Okay, phi m of sine omega t into cos of alpha. So how will I plot it basically? So I am plotting with respect to alpha. So if I, for a particular time instant t equal to 0, the flux waveform will be something like this, right? But you see the peak of this cos alpha is also varying, right? So this peak will vary. So it will vary. Peak will sometimes be higher depending on the instant at which I am seeing this, right? Omega t. This will be higher, right? This can go lower. So that's why it is called a pulsating wave. Why it is called a pulsating wave? Because it is pulsating. Its peak value is pulsating. Peak value is pulsating. So it is not rotating magnetic field, it is a stationary wave. Like you see, you observe, right? There is no phase shift. It is a stationary wave. So that's why we get a stationary wave. What is the problem with stationary wave? We will understand that. So stationary wave does not have a starting torque inherently. I will prove it to you as well. I will prove it. Why does a stationary wave does not have a what do you call starting torque? Okay, how? So what we can do is like this. We have already done. So I will not explain here. This is already done. Alpha is rotating. This is already done. If I is Im sin omega t, then your sorry, this is not, then your flux, right? If I is Im sin omega t, then your flux will be pulsating in nature. This will be, this will keep on changing, right? Okay, so your flux phi of alpha will be pulsating in of nature. So what is the value of phi of alpha comma t? Okay, that is already I have written over here. It is phi m sin omega t cos alpha. Okay, so phi m is a peak value peak flux per pole. Remember, it is always per pole. Don't forget this thing. Flux is always with respect to per pole. Here I was comparing only a single pole. Okay, now like is this a like can I write this in some other format, because I want to come to a conclusion. So I know what is sine A cos B. Sine A cos B, sine omega t, sine A cos B is what? Sine A cos B is basically sine A plus B plus sine A minus B, right? By 2, divided by 2 sine A plus B plus sine A minus B. So basically the sine B cos A term will get cancelled and I will be only left with sine A cos B. Okay, so this is my value basically. Now what I can do is yeah, can I break it down? Yes, I can break it down, right? I can break it down. So this will be phi m by 2 into sine of omega sine A plus B, right? So sine A plus B sine omega t plus alpha and minus sine omega t minus alpha. Okay, so is this something familiar? Sine omega t plus alpha, sine omega t minus alpha, is this something familiar? Yes, if you remember, this was something familiar, right? Here we knew this was a rotating field rotating with a speed of omega, right? Because if I equate this equal to 0, d omega t minus alpha equal to 0. So if I differentiate this, d omega with respect to time upon dt will be equals to sorry, this will be omega will be equals to d alpha by dt. okay, d alpha by dt. Okay, so yeah, this is it. Now this will be my omega t, my plus alpha will equal to 0. So d alpha upon dt will be equals to minus of omega. Okay, d alpha upon dt is equals to minus of omega. So yeah, so basically what do I understand, that I am getting two rotating magnetic field, combination of two rotating magnetic field which are rotating at a speed of omega only, but one is rotating in the clockwise, another one is rotating in the anti-clockwise. So basically I can say that a pulsating standing wave is a superposition of two rotating magnetic field, each rotating in opposite direction. Okay, so inherently there is no starting torque inherently. Why? Because inherently if you see that I'm getting, it is just like induction machine, but two induction machines. One is able to produce, like if I plot the torque speed graph, so the normally the torque speed graph for an induction machine, if you remember, was this, right? So this was a starting torque, then we got a point of maximum torque, then it reduced to this, correct? It went to 0 at around speed ns, right? Around speed ns, the torque will be 0 basically. Speed ns, the torque will be 0, and in the opposite side the torque was something like this, if you remember, right? Something like this. Now this was the torque developed for a induction motor rotating with speed omega, but what if it is opposite? So graph will just be flipped, so the other will be like this. Okay, this will be the other one. Sorry, this will go to 0 around speed what, minus ns, because it is rotating at a speed of minus omega. Okay, and this is plus ns, and then again it will be like this, right? So the overall torque is a combination of these two torque. Now remember, both of them are equal and opposite because their peak value are equal, right? So both magnitudes are equal. Magnitudes are equal. Okay, their magnitudes are equal. As their magnitudes are equal, the torque produced due to them also will be equal, right? Magnitudes are equal, so torque produced due to them also will be equal. Okay, so that is the case over here. I hope you have understood this basic point. So so what will be the superposition? Because torque will be combination of these two, because it is a superposition, right? It is superposition, addition. So overall torque here at the starting will be 0, right? Because this is plus t starting, this will be minus t starting. So overall it will be 0, and then this forward field, like it is combination of two fields. One is known as forward field, this one is known as the forward, that is rotating in the forward direction. So that's why it is known as the forward field, and the other one is rotating at the backward direction, that is why it is known as the backward field. Okay, so what will happen over here is that, as I see on the right hand side, forward field is much higher than the backward field. So torque will be like, if I give it some starting torque, right, then automatically that for due to the forward field, the torque will be much higher, and again it will be 0 somewhere before ns, not exactly at ns, because here I have some negative portion, right? So before ns it will go to 0. Same for the left hand side. Okay, like this motor can rotate in both sides, either forward or backward, depending on which position I'm giving the starting torque, right? That is the important portion. On if I'm giving a starting torque in the clockwise direction, it will rotate in the clockwise direction. Otherwise, if I give it a starting torque in the anti-clockwise direction, it will rotate in the anti-clockwise direction. So this is called as the motoring zone, and this is called as the reverse motoring, because it is not actually rotating in the same direction, it is rotating in the opposite direction. So reverse motoring. So let's say if, like, this is my operating region. Now let's start a discussion if my motor is in the operating region. So let's assume that motor is rotating in the clockwise direction, right? So motor is operating in uh, motoring mode. Motor is operating in motoring mode. Let's assume this. So if motor is operating in motoring mode, remember we will do the analysis like a induction motor only. We will do the analysis like induction motor because it is easier that way, because we have already learned everything. So if my rotor is here, there will be two fields. One will be forward field, another one will be backward fields. Okay, forward field, backward field. Okay, now let's understand what will happen in the rotor's perspective. We know rotor also, like, due to this flux, right, flux cut is there. So if the rotor is rotating at a speed of nr, right, because it is just like an induction machine, it will not be exactly equals to ns, otherwise there will not be any flux cut, right? So it is rotating in the speed of nr. So what will be the frequency of the current induced in the rotor? So frequency frequency of rotor current. Now there will be two components. Again we will assume with superposition there are two components. One is due to this forward field, other one is due to this backward field, right? So there are two components. So let us first solve for the forward field. Okay, let us first solve for the forward field. Now for the forward field, what is the slip? Because frequency is dependent on the slip, right? So what is the slip? Obviously the forward field will rotate with the speed of what? With the speed of ns, right, in the clockwise direction, and the backward field will rotate with the speed of ns in the backward direction. So it is actually minus ns. It is minus ns, remember that. So if I'm writing like this, right, this ns, that means it is same as writing right hand side with minus ns, right? If I say current here is 5 ampere, can I say it is minus 5 like this? Same, right? Same. I hope that same analogy I have used here, right? So So basically basically what is the frequency due to the stator, due to the forward field, forward field, right? Stator forward field. So it is rotating with nr on the same direction, and your forward field is rotating with ns. So what is the slip? Slip definition will not change. It will be ns minus nr divided by ns, correct? So the frequency of the forward field is s into f, right? The slip frequency into slip into the frequency of the stator currents, that is f. Now what about the backward field? Backward field is kind of interesting. So for the backward field, we know that the forward field slip SF, right, was this. Okay. What about the backward field slip? Backward field slip, remember your speed has now become minus ns, right? So speed will, this will be minus ns, this will be minus nr, this will be divided by ns. So with respect to s, if I want to compare, like this is equals to s only, right? This is simple s. Okay. So yeah, so I can write here that SB, so SB is what? SB is can I write this in a different manner? So what is my S basically? S is this value, right? So if I add and subtract ns, so this will be minus ns minus ns plus ns minus nr divided by ns. Okay. So okay, something, am I doing something here wrong? Okay, what is the relative speed here? Sorry, sorry, I made a mistake, right? So your slip, right? Okay, sorry, slip, your slip value, this your slip of the backward field, it was always equals to relative speed divided by ns. So what is the relative speed here? So relative speed, if I see, it is nr plus ns, because it is rotating in the opposite direction. It is rotating in the right hand side. So if I say this one is rotating here, this one is moving with 1 meter per second on the right hand side, and the other, let's say other person is moving with 2 meter per second on the left hand side. What is the relative speed between them? How fast they are changing? So it is changing by 3 meter per second, right? 3 meter per second. The relative speed is 3 meter per second. If this one, this already have explained in induction motor very well. 1 meter per second, and this one is moving with 2 meters per second. What is the relative speed? Relative speed is 1 meter per second on the right hand side, right? Because this minus this will give me 1 meter per second to the right hand side, correct? So yeah, I hope you have understood this point. Basic point you have understood. So this will be what? This will be ns plus nr divided by ns. Okay. So but my slip value is this, right? Yes, I want to write this in terms of my slip. How will I write it? So this we can write, this will be if I write minus ns and plus ns plus nr divided by ns. So what? Okay, let me just rewrite this thing. So I will rewrite this. This will be SB will be equals to ns plus ns minus ns plus nr divided by ns. So this will be equals to, remember this will be 2 because this is 2ns, and this is minus. If I take the minus common, it is same as ns minus nr by ns, right? I want to get back to my slip, so this will be 2 minus s. I think we have done something like this previously as well, during braking, explaining the braking concept, right? So there was also the braking slip was 2 minus s, right? Here also the slip become 2 minus s. Okay, so due to the backward field, the frequency will be two minus s into f. This will be the frequency due to the backward field. Now, very interesting fact to note. Obviously, I know that current in the rotor will be something sinusoidal, right? Due to the forward field, it will be something sinusoidal, that we already know. Okay, so current in the rotor will be something sinusoidal. What about the backward field? So the backward field, this was with the frequency SF, right? So this is due to the forward field. So I'll draw with the same color, SF. Okay, so this frequency was SF. Okay, now the backward field is 2 minus SF. Is it greater or less than this? So we know at full load, right, slip is generally how much? Slip is like 0.1, 0.05 or 0.04, something like this. So 2 minus 0.04 will be higher, actually greater than 1. So the frequency is very high. So 2 minus s into f will be much higher than normal frequency. So it's a high frequency current. So the backward field actually is producing a high frequency current, okay, whose amplitude will be lower. I will show you, okay, I will show you, but generally understand this: high frequency current, amplitude will be lower. Reason also I will give you the reason why the amplitude will be smaller. Just for a second, assume that amplitude is smaller, so frequency will be much higher, so it will just overlap the, give me 1 second, the low frequency current. So basically the rotor current will be noisy, so the flux in the rotor will be noisy. It will not be purely sinusoidal, so there will be noise and harmonics due to this. So that's why the single phase motors have possess more harmonics. Okay, they are more noisy and they possess more harmonics. Okay, so I hope you have understood this point. So like, let's go through and read few things whatever we have discussed. So this is the first thing: single phase induction motor actually are used everywhere, in your fans, everywhere else, wherever you see single phase induction motors are used. Okay, inherently they are not self starting. Why they are not self starting? I have explained you why they are not self starting. Okay, now to make them self starting, what we do, we actually have two kinds of winding. One is the main winding that we discussed. Another one is the auxiliary winding. So both of them will take supply from the same point, but what we will do is we will provide a phase difference. So both of them will provide flux, right? Auxiliary and main, but the difference will be, there will be phase difference, right? Sine of the angle between auxiliary winding and the main winding. So there will be a phase difference. So if there is a phase difference, that basically means, that here there will be a torque, because torque is proportional to the interaction of the two flux and the angle between them. So we want to make the angle between them, we want to create a phase difference so that I can get a starting torque. Then what we do, then we turn off the switch, then only this running winding is energized, the auxiliary winding is not energized. So this one is the start winding or auxiliary winding. Okay, so this is the basic basic working principle of a single phase motor. So when will this be maximum? When sine of angle is maximum, when it is 90 degrees. When it is 90 degrees, it is maximum, right? So that point it will be maximum. Okay, so now one important point, like, so the same thing, stator windings, main and auxiliary. To overcome this lack of self starting, main winding is the running winding. This winding carries the primary current and is responsible for continuous operation, so the rating will be higher. So here the current value will be higher. Okay, so it has to be a thick winding. Okay, auxiliary winding, generally 2/3 of the stator slots, right? There will be slots in the stator, right? This is just a pole, but actually there will be slots in the stators. So 2/3 of the stator slots, I hope you remember what is slots, will be typically allocated to main winding, and the remaining 1/3 will be allocated to auxiliary winding. Okay, that is the general rule of thumb. Okay, so this winding is designed for higher resistance. Why higher resistance? Because if you remember, your slip is proportional to what? R2 by X2. So I want the slip to happen at starting. So of course I have to increase my R2, right? When R2 is equals to X2, then slip will happen at starting. So I want a higher resistance winding at the starting. That's why this winding has higher resistance and lower inductance. Okay, to create phase difference in the current from the main winding and the auxiliary winding, its primary purpose is to generate a starting torque about 1/3 of the stator slots for the auxiliary winding. Okay, so yeah, the auxiliary winding is typically disconnected from the circuit once the motor reaches 70 to 80% of the synchronous speed. So when we will study about different types of single phase motor, there we will see that we are disconnecting the auxiliary winding, because auxiliary winding is there only for starting, it is not there for any other purpose. Okay, however, in some applications like ceiling fans, the auxiliary winding often with a permanent capacitor remains continuously on. Okay, in few cases there is no point of removing the auxiliary winding, that can like be costly. So we don't want to provide that provision, so we directly keep the auxiliary winding on. With auxiliary winding being on, it will also rotate, but maybe the torque production might be lower. Okay, maybe the efficiency might be worse, but there is no problem. We can keep the auxiliary winding on as well. This we will see in different types of single phase induction motor. So generally the space angle, right, between the auxiliary and main winding, we try to keep it 90 degrees to get maximum torque, right? So then torque will be maximum. As I mentioned, torque is proportional to sine of angle. So if sine 90 is there, so torque will be maximum, correct? The flux that we get is a pulsating flux that we have already discussed if I provide a single phase AC supply. According to Lenz's law, any current induced in the rotor will create a magnetic field that opposes the change in the flux, causing it. Okay, in a stationary rotor under a pulsating stator field, the induced rotor flux will always be directly opposite to the stator flux, meaning angle between the rotor and stator will be 0 or 180. What do I mean by it? If you see this explanation, same explanation right here. So if I copy this explanation, so this was the stator flux, right, that we discussed. This was the stator flux, and what have I told you regarding rotor flux? I will just explain. So here, if I show you, this was the stator flux, right, at this point. Now what will be the rotor flux? Rotor flux, according to Lenz's law, will always oppose, right? So stator flux is in this direction, rotor flux will be in this direction. Try to make it 0, right? If the stator flux is reducing, rotor flux also will reduce. Again here it is reducing, rotor flux also will reduce. Again here it is reducing, rotor flux also will reduce. It is in opposite direction, so rotor flux also will be in this direction. So either the angle will be sorry, if here stator flux is increasing, rotor flux will increase in the opposite direction. So what is the angle between the stator and rotor flux? Are you observing the angle? So angle here is 180 degrees, right? 180 degrees. And sometimes the angle will be 0 degrees. Either it will be along the same direction or opposite direction. When same, so let's say this stator flux is reducing. Okay, it is reducing. Stator flux is trying to reduce, right? So rotor flux will try to make it increase. So rotor flux also will be in this direction, but it will try to increase the flux because rotor opposes the behavior of the stator. So if the stator field flux is in on the right hand side, but it is reducing, rotor will provide additional flux in the same direction to increase it. Okay, so the angle will be either 0 degrees or 180 degrees. Angle between the stator flux and the rotor flux will be 0 degrees or 180 degrees. Okay, so what is the sine of 0? Sine of 0 is simply 0. Sine of 180 is simply 0. So the torque produced will be 0 because torque is proportional to sine of angle between them. Angle between the rotor flux and stator flux. Okay, so I hope now you have understood this point. So same thing like this, whatever we have derived, right, that my flux is a combination of two fluxes, forward field, two rotating flux, forward field and backward field, that actually is defined by this revolving field theory. That's it. This is the revolving field theory, nothing, right? There is nothing special about it. This is the revolving field theory. Okay, so revolving field theory, the concept of a pulsating magnetic field that can be mathematically visualized as a superposition of two oppositely rotated magnetic field is known as revolving field theory. So decomposition, a single pulsating magnetic field can be resolved into two counter revolving magnetic field. Counter means opposite direction of equal magnitude, each rotating at synchronous speed in opposite direction. So standstill, the torque will be 0. Overall torque will be addition of both the two torques. Here I have plotted the torques. Okay. So okay, this already we have discussed. So that's it basically. This is the working principle of a single phase induction motor. That's it. Nothing special. Starting torque, again we have to exert a external force like auxiliary winding to provide a phase shift that will develop a extra torque with some small initial torque so that the motor initially rotates. So that's why if your fan stops, you just push the fan and suddenly it again starts, right? So maybe there was a problem with the auxiliary winding or something, right? So yeah, so as the rotor gains speed in forward direction, then it will operate normally, because I am observing that here if the speed is high, then the torque is also positive. Okay, so that is the case over here. The rotor slip with respect to forward field SF decreases, the rotor slip with respect to backward field SB increases, right? Because if S is increasing, your 2 minus S will reduce. And how is it 2 minus S? We have already derived, right? So the change in slips causes the torque produced by the forward field to increase significantly. You see, right? Torque produced by the forward field will be much higher than the backward field. The difference in this torque is the net positive torque in the direction of the rotation, allowing the motor to accelerate to its operating speed. Now remember, the amplitudes of the MMF are not equal to each other. Basically, the amplitude of the forward MMF and the backward MMF are not always equal except starting, because at starting the torque is 0. So flux by the forward MMF and the backward MMF will be not MMF, sorry, flux amplitude. MMF always will be equal, MMFs always will be equal, flux magnitude will not be equal. MMF is what? MMF is current into number of turns. So current is always constant in the stator field, right? So MMF produced will be always equal. But the flux amplitude will not be equal. Why it will not be equal? I will explain. So MMF will be equal. MMF always will be equal. Okay, so the flux amplitude will not be equal. Flux amplitude of the forward field and the backward field will not be equal. Why they will not be equal? uh, so mmf is depending on the stator current and the turns, right, which is same magnitude, because magnitude of the stator current is same, right? So this will not change. Number of turns also will not change. It's a mechanical parameter. The corresponding flux amplitude are only equal at standstill. Why? As the rotor speeds up, the effective impedance of the rotor windings to the backward field changes. Because do you remember what was the rotor resistance with respect to slip? It was R upon S. So for the forward field, this is the resistance. For the backward field, what is the resistance? It is R2 upon 2 minus S. So of course the slip, this one will be much higher. This one will be much lower, right? So here this resistance is much higher. This resistance RF is much higher. If this resistance RF is much higher, then the drop, right, EF will be much higher, and due to this the flux magnitude will also be much higher. But here the drop will be much lower because the resistance RB is lower. And like this is my circuit, I will show you the circuit. Okay, I will show you the circuit. So I provide a voltage here in the stator windings E1, and then I will have two windings like this R2 by S and R2. I will show you the equivalent circuit just in a few slides. R2 divided by 2 minus S. Okay, so here of course E is constant. So if this is higher than this, so here there will be more drop, right? More drop there will be than the backward field. So if there is more drop in the forward field, so flux also produced will be higher. Okay, so that's why the flux amplitude of the forward field will be much higher than the backward field. Okay, so I have explained it over here. So I hope that is clear now why it is much higher. So if the flux is higher, then the current amplitude also will be much higher. The flux produces current amplitude, that also will be much higher. Okay, and here as the flux is much lower, then the current amplitude also will be much lower. That's why you have seen that now remember, of course you cannot directly measure the backward current and the forward current because it is superposition. So your waveform will be something like this, right? You cannot directly separate out. Mathematically you can write it, but if you go and actually run the motor, it will be a combination. Okay, so I hope now the reasoning is clear why the current is lower here and the current is higher here. Okay, so same thing I have tried to explain over here. Why is the EMF amplitude higher here and lower here? Due to the resistance. Okay, because both of them will provide different resistance. Okay, so yeah, I hope that is clear. I don't need to explain much here, but one more thing is there. The forward field, remember what is the frequency of the induced EMF? Because remember this was the equivalent circuit, but actually the frequency of the induced EMF is depending on the slip, right? So if my slip is very high, right, that is 2 minus S into F, right, then that means the inductance, leakage reactance also will be very high, right? For the backward field, XP will be much greater than the XF. So that's why this actually considerably degrades my power factor. Here power factor degrades considerably, right? So due to large rotor current, the power factor will degrade considerably. Very poor power factor. Very poor power factor for the backward field component. Okay, so backward field component, the current of the backward field component will have much poor power factor than the forward field component, and of course as stated they are anyways equal, so I don't care about that. So yeah, I hope now it is clear why is the forward field current amplitude is much lower than the backward field amplitude, or the what do you say, or the induced EMF. Okay, so yeah, XB will be much higher than XF, so this will produce even worse power factor. Or you can understand it like this, that your, like, what is your rotor side comprises of? It is R2 by S into X2, right? So here R2 by S is very small at full load. So this R2 will be R2 by S will be much larger than X2. So here the power factor will be much better for the forward circuit. Like there will be two circuits. I will just draw the equivalent diagram. There will be two circuits. So the forward circuit will be much better than the backward circuit. Right? In backward circuit, what is the resistance? Resistance is R2 by 2 minus S, which is actually pretty low because this value will be something greater than 1. Now if this value is something greater than 1, this value overall will be something pretty low. That means power factor will be poor compared to the forward field. Poor compared to forward circuit. Okay. So again, losses will be there, like vibration and noises. Why? Because due to the core loss, because of course here core loss will be higher. Why? Because the frequency has increased. Core loss is proportional to frequency. So due to the backward field, remember in the core rotor side, the frequency has increased, right, due to the backward field. So if frequency has increased, the core loss also will increase. So first of all, losses will be higher here in single phase motors, but like it has a very good flexibility. That's why we use this in regular application. Okay, not in high efficiency application, but in regular application, core loss will be higher, so the frequency also will be higher. Okay. Yeah. Compared to three phase motor of the same rating. So core loss will be higher. Again, due to the pulsating torque, there will be noises. Why? Because the stator current, high frequency current is there in the backward field. That high frequency current will produce high frequency flux that will in turn generate noise. So noises will be there. Okay, this already we have discussed. Due to the pulsating torque, noises will be there. Okay, what I have here, right? These inherent pulsating torques. Why? Because remember the relative speed between the rotor field and the rotor forward field and the stator forward field is 0. That is what is written over here. The relative speed between the rotor forward field and the stator forward flux is effectively 0. They will rotate together, right? The relative angle between the backward stator flux and the backward rotor flux is effectively 0 because the backward rotor flux, due to the backward stator current, okay, remember there are two currents. One is this current. In the rotor there are two currents, right? One is this current. Where did it go? One is this current, another one is this current. So this current will produce a forward rotating field and this current will produce a backward rotating field, right? So that field and the backward field will have zero phase difference, zero angle difference between them. That will be constant. Okay, that will be always constant. But the problem is between the forward stator flux and the backward rotor flux. So backward rotor flux is rotating with the speed of NBR and the forward stator flux is rotating with the speed of NFS, right? So there is actually a relative speed between these two. But average torque will be 0. Why? Because let's say this is the angle, right? Let's say this is my backward rotating flux and this is my forward rotating flux, NFS and NBR. Okay, so initially let's say the angle was some value, let's say 45 degree. Then again you're observing both of them are rotating in the opposite direction, so the angle between them will increase. So at this point somewhere it will come here, then again it will further increase, it will come here. But now you're observing this actually is angle is reducing because it is always the angle with respect to the internal angle, right? The acute angle basically. Okay, so here the angle is reducing. Initially it was like here the angle was increasing, then it became 180 maximum, then it will reduce, then the torque produced will be opposite. Okay, so it is reducing. So again at certain point both of them will be in the same phase, and then again the angle will be increasing. It will come here, it will come here. Okay, so what is happening? Overall the average angle is 0. So overall the average torque due to this, right, will be 0. Okay, but in between when the rotor is rotating, still it is producing some torque, because still the angle is not equals to the angle between the forward rotor field and the backward stator field is not either 0 or 180. It is sometimes 10 degree, 20 degree, 25, 30, something like this, right? So it is always keeps on changing. It keeps on changing. If it keeps on changing, that means the torque also will keep on changing. So for a certain second, torque will be somewhat positive, then it will reduce, then it will be negative, it will go more negative, and then again it will reduce from the negative. So torque also is pulsating. So I will get a pulsating torque. So the pulsating torque, the average of that pulsating torque will be 0. The average will be 0. That is what I have written over here. But still there will be vibrations. If you could not understand this explanation, you can understand this with the help of this current. So this current is a high frequency current. Due to high frequency current, there will be a high frequency noise, and those noise are nothing but basically torques, because current produces torque, right? I was supposed to get a pure sinusoidal waveform, but I am getting a sinusoidal waveform superimposed with high frequency current. So if high frequency current is there, that means that current also will generate a torque, but overall I see it is pulsating, it is very fast, and it will be this like this, right? My motor is overall rotating, so the motor will rotate in the clockwise direction, but with bit of vibrations, so this vibrations is denoted by the currents, and overall this waveform determines the overall rotation. So overall rotation is like this clockwise, but due to some vibrations it is rotating, right? These vibrations. Okay, so that is the problem over here. So I have given you two explanations. Even if you could not understand the previous one, this one I hope is clear to you. Due to the current we are getting that vibrations. Okay, so yeah, that I hope that is clear now. So why it will be more noisy? So single phase motor, the conclusion is single phase motor will have more noise, more losses, more core losses, because copper loss will be lower because the current is lower and is a single phase, and it will have more noise. Okay, so that is the case over here. I hope you have understood this point. So now yeah, so this is my poles and speed. I hope like poles, so this is the difference between single phase and three phase, but still we will use three phase, because still we will use single phase because the construction wise it is very easy, like just like induction, and it is light. For light loads, right, we don't need three phases. So for light loads, single phase is enough. So that's why we use single phase motor only in light loads in our homes, everywhere else. Okay, I hope it is clear. So one more thing about poles and speed. The speed of an induction motor we know is inversely proportional to the number of poles, right? And this is an induction motor only. It is a single phase induction motor, right? So therefore a motor with fewer poles will have higher speed, and a motor with higher poles will have higher poles will have lower speed. Here, as few of the windings are used in auxiliary winding, okay, so number of poles of the single phase motor will be lower than the number of poles of the three phase induction motor. Why? Because few windings are getting used as auxiliary windings, so these are not taking participation in the pole. So number of poles also, one more thing, one more comparison, number of poles in auxiliary winding, sorry, in single phase motor will be lower than 3-phase motor. Okay, so I hope it is clear now. So I hope this thing is clear. So now one more thing I want to discuss is how can we reverse the direction of the rotation. How can we reverse the direction of rotation of our uh, single phase motor? If I want to reverse it, how will I reverse it? So circuit wise, the diagram will be somewhat like this. Here I will have main auxiliary winding. Okay, I am not drawing the resistances, and here I will have a auxiliary winding. Right? Both of them will be in parallel only, because if you remember here, right, this is the physical circuit. Both of them are actually connected across the same supply. So both of them will be kind of parallel, and rotor side will be in between. This will be the rotor. Just drawing the rough circuit here, not the exact one. Okay, not the exact one. So rotor circuit I am not drawing. I'm not referring the rotor circuit for now. Okay. Now the thing is, if both the windings are there, so this is the main winding. This is the main winding. And this is a auxiliary winding. So now what I can say is, how can I change the direction of rotation? So what is the torque produced? So torque produced will be something like this. Torque produced will be the mmf due to the main winding, mmf due to the auxiliary winding, into the sine of angle between them. So if somehow I can reverse the direction of the mmf, that also is enough. How can I reverse it? So simply what I will do, right, I will either reverse the terminals. This I will connect it here, sorry, not here actually. This I will connect here, and this one I will connect here. Okay, so I will reverse the connection diagrams. If I reverse the connection diagrams, then the field mmf produced due to the auxiliary winding will just be opposite. So the torque will be now negative. Negative means opposite torque. So it will rotate in the opposite direction. So either if I replace the main winding terminals, reverse the connections, or if I reverse the connection of the auxiliary winding, that will reverse the direction of the rotation. But please don't reverse the main supply. That will not work. Okay, but if you reverse both the main and auxiliary winding, that will not work. Or if you reverse the main supply, that will also will not work. This is exactly similar to DC series machine. If you remember how to change the direction of rotation, this we have already covered. That's why I'm going a bit fast over here. So the direction of rotation of motor, rotation of motor direction of rotation of motor is equals to, can be changed either by reversing the auxiliary winding terminals or main winding terminals. Okay, but make sure but make sure we are not reversing both auxiliary winding or main winding. Okay, auxiliary winding and main winding, right? If you reverse both, it will not work. Or we are like reversing the supply or reversing the supply terminals. Okay, reversing the supply terminals. I hope you have understood this point. So yeah, this is how we can reverse the direction of rotation, how we can change the direction of rotation. Okay, so now let's understand the equivalent circuit of a single phase induction motor. What will be the equivalent circuit? So remember, this circuit is with only main winding. So this circuit is with respect to basically when the motor is operating, right? It is not starting, when only main winding is connected. Okay, we are not discussing about the auxiliary winding, because auxiliary winding we will mostly only be discussing when it is starting, right? After it has reached steady state, then the equivalent circuit will be this. Why? Because I have told you, right, according to the revolving field theory, my motor is a single phase induction motor is a combination of two fields, forward field and backward field. So due to forward field there will be some induced EMF, due to backward field there will be some induced EMF, and the forward field will see a different rotor resistance, the backward field will see a different rotor resistance, because the slip is different. Jx2 also will be different. Now this is the equivalent circuit. Basically it is the superposition of two rotor circuits. Okay, now the important fact to note here is that sometimes generally the circuit will be given to you. Sometimes this is also R2 by 2s for proper symmetry, R2 by 2 minus R2 by 2 into 2 minus s. Okay, sometimes it is there. This is written as x2 by 2, it is written by as x2 by 2. Okay, there is no standard format. Gate exam they will give you what is the, in gate exam they will give you what is the like what this means, because you can assume it to be R2 by 2s or R2 by s, both actually will work, no problem, but they should actually provide the circuit diagram. Otherwise you will be confused, because in few books they have written R2 by s, and this will become xm will become x2 xm by 2, and this also will become xm by 2. Few books they all are divided by 2, in few books it is just written R2 x2 R2 x2 like this. Okay, so it all depends how they are writing down the values. Okay, so generally I hope circuit diagram will be given to you. Okay, so that is clear. Now one more thing, if you observe here, if my NR is increasing, that means my slip is reducing. If slip is reducing, this value will be much higher than, sorry, this value will be much lower than this value. So most of the drop will occur across the EF. So EF will be much greater than EV, because R2 by S will be much greater than R2 divided by 2 minus S. Okay, because this is almost equals to 1. So I hope it is clear to you why is that the case. Now sometimes you have to find out few values. So I have already told you that your flux is proportional to EMF, right, induced EMF. So I can write this equation that EF by backward EMF induced EMF will be proportional to the flux by the forward and the flux by the backward. Okay, and what it is proportional to, what is it proportional to? So here, right, if I convert this into a singular impedance known as ZF, and if I convert this into a singular impedance known as ZB, I hope you can do the equivalent impedance, then I know it is just simply a voltage divider circuit. It is just simply a voltage divider, because current here is same, rotor current will be same, right? So current across both of them are same. So their voltage ratios will be proportional to their impedances, right? So this will be ZF by ZB. Okay. So that is the case over here. So this is also another very important relationship that you must know. So if they are asking you the flux ratio of the forward field and the backward field, you just simply have to find out the impedance ratio. So this will be basically magnitude, right? Magnitude, because phase we will not take care of. Magnitude will depend on it. Now let's discuss one more thing regarding the power. So what is the air gap power of the forward field? It will be simply I2 forward current, whatever current is flowing through the resistance I2F, right, whole square into R2 by S, and whatever current is flowing through the resistance here, that is I2B, right, I2B whole square into R2 divided by 2 minus S. Okay, so yeah, that is the case over here. I hope you have like this is simple, right? It is just like 3-phase induction motor. We are just revising 3-phase induction motor, but just there is superposition. So I am writing two things here: forward field, backward field. What will be the torque due to this? Torque due to the forward field will be what? PG divided by omega S, right? PGF divided by omega S, and torque due to the backward field will be PG backward divided by omega S. Okay, backward divided by omega S. And what will be the net torque? So net torque, again remember, net torque will be the sum of the two torques, right? F and TB. Sorry, this would be negative, right? This will be TF minus TB, that will be negative. So net torque is negative because the backward field will provide a opposite torque, as we can see from the graph itself, right? Backward torque in the same speed, backward field is providing a opposite torque, negative torque, and forward field is providing a positive torque, right, in the same direction. So it will be minus. Now what is the mechanical power developed? What is the P mechanical? So P mechanical will be the like, if you remember, in induction machine, what was the normal formula? It was 1 minus S into PG, air gap power. Yeah, this would be equals to what? Simply I can write my P mechanical, because the backward field would be opposing, so it will be PGF forward minus PG backward. Okay, so that will be the overall mechanical power output at the shaft. Okay, I hope it is clear. So we have got all the formulas. It is just a revision of the induction motor, that's it. So now let's solve this question. So a single phase 4 pole, sorry, like the tablet got crashed. So a single phase 4 pole, it's a single phase 4 pole induction machine. So 4 pole induction machine draws a line current of 60 amperes. Okay, it is drawing a line current of 60 amperes minus 70 degrees at standstill. So at standstill it is drawing this much amount of current with its main winding supplied from this. So whatever we are discussing about with main winding connected, with auxiliary winding open, right? Okay, so main winding it is connected. So main winding will have its stator resistance, will have its rotor resistance, reactance, stator reactance. Then it will have the resistance of the rotor side for the forward field, and there will be reactance x2 as well. Then I will have another resistance for the backward field, and then another reactance, right? Exam I'm ignoring because here also they will not provide you the exam. Okay, neglecting stator impedance they are neglecting. So of course I have to neglect this one. I don't have any R1 JX1, that's it. No R1 JX1. Okay, impedance they are neglecting. Magnetizing current, so there is no parallel branch and the rotational losses. There are no rotational losses. Calculate the torque developed when the slip is 0.05. What is the torque developed? Right? They are asking me what will be the torque developed. So can I find out what is the overall impedance here? Z. So Z will be equals to V upon I, because I am providing a voltage of 230 degrees. volts. Okay, so it will be voltage by current. Okay, this will be equals to 230 volts divided by current. So current I is R2 divided by S, whatever this impedance, this is the, sorry, R2 divided by current. Current is given to me 60 angle minus 70. Voltage is phasor 0. Voltage is the reference, right? So this value will come out to be, impedance Z will come out to be 230 divided by 60, that is 3.833. Now it's very important to understand, actually they should have shown you the this equivalent circuit, right? Sometimes in the equivalent circuit it is x2 divided by 2, r2 divided by 2. Sometimes it is just r2. So because like I have the solution, so in the solution they have assumed it to be r2 divided by 2. So like the best thing will be if you assume the equivalent circuit here, right, to be divided by 2 only. Like otherwise, like you choose this by default, okay, if nothing is mentioned, because there is a confusion. Both are totally fine, but actually they should provide the circuit. Sometimes in the question circuit is not provided, so by default you will choose this r2 divided by 2s, r2 divided by 2s minus 1, x2 divided by 2, x2 divided by 2. Why have I chosen this? Just for simplicity, this is easier for me to explain, because here I am seeing total symmetricity. Okay, this is also symmetric, but it is more easier for me to explain. That's why I had chosen a circuit like this. So yeah, so what you do is you choose here, because it's a standard textbook question, and in the textbook they have chosen r2 divided by 2. So by default you will choose this r2 divided by 2, r2 divided by 2s. Okay, okay, so now what will be the values here? So I have got, this is my impedance, right? What is the power factor? Power factor is plus 70. So I can break this down into real and imaginary part. So what will be the real portion? So this into cos 70 will be, that's 2 less, right, 1.311, and sine 70, right, sine 70 is into 3.83. so sine 70 into 3.833, that is plus j 3.6. okay, that is plus j 3.6. so here this is plus j 3.6. so what will be my r2? Basically r2 will be equals to 1.311 and x2 will be equals to 3.6. so what is the pg of the forward field? Because they have asked me torque, so for finding out torque I have to find out the forward field torque and the backward field torque. So pg of the forward field will be simply I2 square into R2 divided by, now remember they are asking me torque developed at slip equals to 0.05. okay, so R2 divided by 2 divided by 0.05. so R2 divided by 2 into 0.05. okay, now one more thing, at standstill the current is this is the standstill current actually, but you don't know the current at this slip. So you have to again do the calculation. draw the circuit at this, because when slip is equals to 1, then this is R2 divided by 2, this is R2 divided by 2, because this is also 2 minus 1, that is 1. So R2 divided by 2, R2 divided by 2, so that is R2, and this is X2 divided by 2, sorry, this will be X2 divided by 2 and X2 divided by 2, that is X2. Okay, so R2 divided by 2, R2 divided by 2, and X2 divided by 2, X2 divided by 2. Okay, so now what I can do is, this is not the current, I have to find out the current, so I have to draw the circuit at this value of slip. So R2 is this, right? So what will be R2 divided by 2 into 0.05, that is what I have to find out, right? So my circuit will be R2 divided by, let me write, X2 divided by 2 is 1 point, that will not change, X2 value overall will not change, right? So if I write the equivalent circuit, draw the equivalent circuit, this X2 by 2, X2 by 2 also will always will be added, so they will not have any problem. So this will always have this X2, that will be constant because that is not varying with respect to slip. This will be X2 only, that is equals to 3.6. Now what about this resistance? So I will have a resistance which is forward field. Okay, okay, so this is basically R2. R2 is 1.311 divided by 2 and divided by 0.05. So this is 13.11 ohm. This is the forward field resistance, right here, this one. Backward field resistance you will see is much smaller, so that's why the voltage drop also is much smaller in the backward field resistance. So backward field resistance, if you calculate, you will calculate this value, right? It will come out to be 1.311 divided by 2 divided by 2 minus s, so divide by 2 minus 0.05, so it comes out to be 0.3361 ohms. Okay, so this is my R2 back. Okay, so this is my value basically. So yeah, so now can I calculate the new current, because voltage applied is still same, that is 230 volts. So I have to calculate the I2 at this particular slip, right? At this particular slip I have to calculate the I2. So I2 will be equals to let me write the equivalent resistance, that is 13.11 plus 13.44, that is 13.446 plus J 3.6, okay, and 230 volts. So this will be whole square plus 3.6 whole square whole under root into 230. So magnitude is 16.52. What is the angle? Angle, do I need to find out? Angle also, even if I don't find out, that's fine, but still let's find out. So this, right, into R by Z, 3.446 cos inverse is 35. This should be lagging actually, minus 35.53 degrees. Okay, so now I know I2 magnitude. I just have to multiply this by R2F. Remember the forward field resistance. Forward field resistance is this. Can you see how big this is? It's like 30 or like even larger than this, right? 30 times. So the drop here will be huge. So that's why this produces high flux. So previously I told you, right, this will produce higher flux. Now I hope it is more clearer to you why this will produce higher flux. Okay, so this will come out to be equals to, this will be equals to 16.52 52 whole square into R2. R2 is R2F is 13.11 divided by 2 by okay, sorry, okay, already this is okay, sorry, this is R2 divided by S only. So this whole value is 13.11 only, right? Already we have calculated. This whole thing is 13.11. This whole thing is R2F. Okay, so this whole thing is R2F. So this whole thing is 13.11. So this will be my air gap power. So 16.52 whole square into 13.11. So this is 3577.85 watts. Okay, so from here can I find out the forward torque? What will be the forward torque? For that, first of all, I need to find out the okay, let's first find out the mechanical power output, right? From there only we will be able to find out. Okay, torque, right? Actually here net torque is this, but what is net torque equals to? Net torque I can write will be equals to P mech upon P mech net upon omega r at whatever speed it is rotating. I can divide it, or you can divide it by what do you call? You can divide it by omega s as well. If you do it, omega r also will work whatever speed it is rotating. So they are asking me what is the calculate the torque developed. Okay, it is asking what is the torque developed, not the torque at the shaft power, right? So this is a net torque output. What is the torque developed? So developed torque, T developed, right, will be simply air gap power divided by omega s. That's it. Air gap power divided by omega s. So let me write this down. So this is the forward air gap power. Now let me find out the backward air gap power. Backward air gap power will be I2 square into R2 divided by 2 into 2 minus s. So this will be equals to if I want to calculate this value, so what is this value? This value is this 0.3361, right? So 16.52 whole square into 0.3361. So 16.52 whole square into 0.3361. So it comes out to be 91.725 watts, which is very less. So overall my net air gap power will be PGF minus the PGB, right? Because of course the other air gap power will be opposing nature. So overall air gap power comes out to be 3577.88. So it comes out to be 3486. Okay, 0.154, 0.155 watts. So this is the overall air gap power. Now what is the torque? So torque will be simply air gap power divided by omega s, right? So this is 3486.155. Omega s will be if you remember the formula, like omega s you can always write. What is omega s? Omega s is like I also tend to forget. It is omega s is 2 pi ns by 60. Ns is 120 f by p, so it will be 4 pi f by p. So 4 pi into f, 50 by p. P is number of poles is 4. So this is equals to into 4. Okay, 4 anyways will get cancelled. So divide by 4, that is fine. Divide by pi into 50, 22.1 22.193 Newton meter. 22.193 Newton meter will be the answer for this question. Okay, remember this is the developed torque. This is not the shaft torque. Shaft torque is the mechanical power output Pmech by omega r, the speed at which the rotor is rotating. So developed torque is not equals to shaft torque. Shaft torque is the torque output at the shaft. Okay, so let's solve next question. Generally they will give you the circuit diagram. If they don't give you the circuit diagram, that means you have to assume this one by default, this circuit diagram by default, right? This one. Okay, generally your xm and all those things will be neglected, so you don't have to worry about that. So here again they have provided xm, but here we will not calculate xm. If you are in the gate examination, you will ignore xm, okay, because the calculation will be very high. You don't have that much amount of time to solve with xm, right? So the equivalent circuit diagram is given. It is a 220 volt supply with 50 hertz. With 50 hertz, and single phase induction motor is given below the following parameters. Okay, it is given below the following parameters. Basically the stator resistance is 1 ohm, r1 is 1, so this is also the stator resistance only, right? This whole thing is the stator resistance, that is 1 ohm. Okay, rotor resistance referred to stator is 2.5 ohms. So r1 is 1, but then this will be what? This is 1 by 2, 1 by 2, so r1 is given to me 1, right? So overall it will be 1 only, and this is 2.5. R2 is given to me as 2.5. All these values are given. I have just written on the values whatever is given to me. Now friction and windage loss also is given. So friction and windage loss also is given, that is 25 watts. Okay, and core loss, you will see core loss is considerably higher due to higher frequency noise, 100 watts. So they are telling me the motor is operating at a slip s equals to 0.04. Okay, now calculate the following parameters. Stator current, so I have to calculate the stator current. So s equals to 0.05, that's why I have put here 0.05, right? So I will draw the equivalent circuit. It's not like I will solve the equivalent impedance here, the equivalent impedance here, then I will write it down. No, I will not do that. That will be too much time consuming, right? So here is the equivalent circuit with this resistance and reactance added. Okay, so this is the equivalent circuit. Now if I want to further approximate it, I will neglect this. Here I cannot neglect this branch. Why? Because this is 62.5. So like you will put here 0.04, you will see 2.5 divided by 0.04 will yield you 62.5. So this is very comparable to this. The magnitude here is very comparable to this. I cannot ignore it, but definitely I will ignore the reactance because this is much higher than this, so I can ignore this. Here again this is comparable, but this is much high, so I can neglect the shunt branch, right? So roughly if I approximate it in gate examination, you have to understand what things to approximate. If options are present, please don't solve the circuit wholly, approximate things. So here what I will approximate, this will be, and you will see, if you want to calculate, you calculate using this circuit. Okay, you will see you are getting the same, almost same current. Bit of difference will be there, but it will be almost same current. So this will be 1 ohm, this will be 1 ohm, and again I cannot ignore this. This can't be ignored, right? But I can definitely ignore this one. So this will be J100, (62.5 ohm). Okay, then this will be, like, I can ignore this branch, very high impedance, only I will have this branch 1.275 and J3. Okay, so now this will be, so now can I calculate the current? So this is 220 volts, right? 220 volts, 50 hertz. So one more thing again, whatever this value will come out, this will be almost 30 point something, right? So this drop and this drop will be almost negligible. This drop and this drop will be almost negligible. So the whole of the drop will come across this one. So I can assume approximately across this 220 volts will come, because this is negligible compared to this, right? This is 62.500, some 50 like magnitude will be some 50 ohms or something, which is much greater than this. So here the voltage drop will be the highest. So roughly I can approximate that this will be 220 volts roughly. So what is the equivalent impedance here? The equivalent impedance here will be J into 100J into 62.5 divided by 62.5 whole square plus 100 square whole under root. Okay, so yeah, now what you can do is what will be the value here? So this will be 62.5 whole square plus 100 whole square whole under root. So this comes out 17.924, and this will be 62.5 into 100. So this will be 6250. So 117.924, this will be 53. Okay, 53 ohms. And the angle, if I want to calculate the angle, this will be 100 divided by 62.5 tan inverse is 90. So this is 32. Degrees. Okay, this is 32 degrees. So this is my impedance basically. So can I find out the current? Yes, very easy, right? So current will be roughly equals to 220 volt divided by 53, 32 degrees. So this into 220 is 6.874 angle of minus 32. Okay, so I got the current, right? This is my current. I may correct here 53 to 20 volts. Yes, this is my current, no problem. Let me calculate this again. 220 divided by 53. Oh, sorry, this is 4.15. What am I doing? 4.15. Okay, and angle is this. So what have they asked? They have asked me the stator current. I have found out, and the power factor. Power factor is what? Power factor will be, this is the first part. Okay, second part will be power factor. Power factor will be cos of minus 32, right? So this will be equals to 32 cos, sorry, 32.848. remember it is lag because the current is lagging the voltage, right? So it is lag. So we have got these values. If you have doubt, you don't approximate it, you directly calculate, right? Using the equivalent diagram, you solve the circuit, you will see almost you are getting similar answer, almost. Okay, so that is the case over here. Now let's solve this one. What next? They have asked output power. What will be the output power? Output power will be simply the air gap power, right? So there are two powers. One is the forward field power, that is I2 square. Stator current is same. Remember now, what is the current that is flowing through here? I2F. That is also very interesting to know, right? I don't know what is the current that is flowing through here. I have to find out the magnitude. Okay, that is very easy actually, because it is like this 220 volt is directly across this parallel branch. So I know what is the current. I2F will be what? So I2F whole square into R2, R2F, right? I know my I2F will be simply V 220 divided by the uh, divided by this resistance, whatever resistance it is providing, 62.5 at running condition. So it is providing 62.5, 62.5. Okay, $62.5. So this will be 220 divided by 62.5. So this will be 3.52 amperes. Okay, 3.52 amperes. So this is my forward field current. Now I know the resistance. Resistance already we have calculated, right? 62.5. So it's very easy to calculate the power. Forward field power, it will be 4.1, sorry, not this. Current is 3.52 whole square into the forward field resistance, that is 62.5. This will be equals to 3.52 whole square into 62.5. So it comes out to be 774.4 watts. Okay, now the backward field will be the current I2 backward whole square into R2 backward, right? Now remember, whatever current is coming out, same current will come. So whatever current is coming in from here, same current will come out, right? And same current is flowing through the backward resistance. So this current is same as the overall current that we had just calculated, this one. So it will be simply equals to 4.15 whole square. Although the current is higher, but the resistance, right, is much lower. Resistance is much lower, so the power developed will be much lower. So this will be equals to uh, backward resistance, that is 1.275, right? So this will be equals to 4.15 whole square into 1.275. So this comes out to be 21.958. Now remember this thing, that what will be your net mechanical power, right? Net mechanical power. Your net mechanical power, we had already derived that it is equals to 1 minus S into the net air gap power, right? Output, because they have asked me output power. Output power means it's not the air gap power, it's the output from the motor. So output power will be 1 minus S into PG net. Now if you have doubt that how sir this is 1 minus S into PG net, we have other way to solve this as well. So we know, like I can write over here, P mechanical due to forward. P mechanical due to forward will be basically, this is fine, this will be 1 minus S into PGF. But you might have a doubt, sir, how negative sign is coming over here. So what is P mechanical due to backward field? It will be 1 minus slip of the backward into the backward air gap power of the backward field, right? So what is the slip of the backward? If you know, the slip of the backward is 2 minus S. So this will be 1 minus 2. So minus 1 plus S into PGB. So here if I, what will be the overall mechanical power? Overall mechanical power will be the combination superposition of the two. So it will be 1 minus, so PGF minus S into PGF, and this will be minus PGB plus S into PGB. So I can simply take common minus S and I can simply take common 1. Okay, so 1 minus S I can take common. So this will become, if I take common here, okay, no, if I take common here PGF, and if I take common, sorry, if I take common here PGF, and if I take common here minus PGB, this also comes out to be 1 minus S. So ultimately your mechanical power output comes out to be what? Mechanical power output comes out to be PG 1 minus S into PGF minus PGB. So automatically the sign is negative. So we were writing previously minus, but here if I even write plus with superposition, I am able to understand the backward field air gap power will be opposing. That's why it is negative over here. So that is also proof to you why it is negative. Okay. So let's now come back here. Let me come back. So this will be PG net. So this will be equals to 1 minus S, that is 1 minus 0.04, I guess. Operating slip is 0.04, right? If I remember it correctly. Yeah. And okay, one more thing. These are also there, right? Friction and windage and P core power. Okay. So those also I have to subtract. So from the air gap power, I also had to subtract. Okay, no. Coal loss. First of all, from the coal loss, what do I have to subtract? On the air gap, I have this power. Okay, after air gap, friction and windage, all those come, right? After air gap power. So P mech will be this value, PG net also minus the losses, right? I have to subtract the losses, minus P core minus the friction and windage loss, because this was the supposed power that I'm expecting, but I have the coal loss and friction and windage loss, right? So this also will be there. So this value will be equals to PG net. PG net is 774.4 minus 21.958 minus P core. P core is 100 watts minus friction and windage loss. Friction and windage loss is 25 watts. Okay. So overall output power, this is overall output power, because this one is the P mechanical power that it will develop, but from the mechanical power this much will be lost due to coal loss and this much will be lost due to the friction and windage loss. So ultimately your P out will be, if I want to write the P out value, okay, uh, 0.0, so this will be 774.4 minus 21.958 into 0.96, so this will be 722.344 minus 100 minus 25. So okay, overall it comes out to be 597.344 watts. Okay, so this is the output power. Now next, what they are asking, output power we have calculated, this is one of the answer. The torque, they are asking me the developed torque. Now developed torque is different. If they are asking me developed torque is the torque developed before the shaft, right? So shaft torque is different, developed torque is different, right? So developed torque will be this PG net divided by omega S. So this will be equals to, basically this will be equals to PG net. PG net is this value, right? This, so 774.4 minus 21.958 So this is 752.742 divided by 4 pi into F by P. So this will be basically frequency is 50 hertz and number of poles is 4. It is a 4 pole machine, correct? It is a, sorry, it is a 6 pole machine. 6 pole machine. It is just like these questions are just revision of induction machines. That's it. Induction motors, right? So this will be equals to, if I calculate this value, this into 6 divided by 200 into pi. So it comes out to be 7.188 Newton meter. Okay, this will be the overall torque developed, and shaft torque is a different value. What is the shaft torque? Shaft torque will be P mech by omega r, by whatever speed the rotor is rotating, right? So P mech is 597. So actually I will add one more point, also calculate the developed torque, also the shaft torque. P mech I have already calculated 597.344. So it is 5344 divided by omega r. Now omega s is this, omega r will be 0.96 multiplied by this, right? So 4 pi into 50 divided by 6 into 0.96, because 1 minus s, right? That is the rotor speed. So this will be 6 into 597.344 divided by 4 into pi into 50 into 0.96. Okay, so 5.94 Newton meter. So this will be the torque developed by the shaft. Okay, I hope you have understood this point. So this is a different answer, this is a different answer. Okay, this is the developed torque, so this is the shaft torque and this is the developed torque. Both are different things. Now what is the last thing that they are asking? They are asking me the efficiency. What is the efficiency? So efficiency will be what? Efficiency is very simple. It is basically P out upon P in, right? Efficiency is P out upon P in. So what is P in? P out already we know, that is, this is the P out, 597.344 into 100, obviously, into 100 percentage. So this will be 597.344 divided by P in. P in is P in. So input current I know, right? Input current I know, input voltage I know, right? So it will be VI cos theta. So V is 220 volts into I is 4.15 into cos of theta, that is 32, right? So this is V is 220 volts, right? If I am not, yeah, 220 volt, I is 4.15, cos of 32. So into 100. So this will be 220 into 2.1, sorry, 4.15 into cos of 32. So this into 597.344 into 100. Okay, so it will be 77.1515 percentage. Okay, so yeah, this is the answer, basically 77.15 percentage. Have I done it properly? I will just again once again calculate 220 into 4.15 into cos of 32. Yeah, this into 597.344. Yeah, 77.15 percentage. This will be the answer of the final question. So yeah, that's it basically for this lecture. In the next lecture we will learn more about the auxiliary winding. Today only we discuss about the main winding. We will learn different types of single phase motors with different types of auxiliary winding. Thank you, and I will see you in the next lecture. Until then, happy learning.